Alright, we are in section 7.7 looking at approximate integration. So when introducing integration, think back to your Calc 1 days. We talked about two different ways of approximating. That was via left-hand approximations and right-hand approximations. And we used these to kind of narrow down the value of the integral, right? So we see in the graphs right here on the left-hand side approximation, right, you create those rectangles that approximate area, and the more rectangles we have, the better approximation we get for that area. And then we can do the same thing on the right-hand side, and we would get a different value for the area, and then depending on the concavity of the graph, right, we might get an underestimate or an overestimate of the actual area. So what we're going to be doing today is looking at different and better ways of approximating values of areas and integrals with different techniques than we saw with the left-hand side and the right-hand side approximations. Now, this might feel like kind of a step backwards since we've already talked about so many techniques of integration, but there are times when doing an integral using these techniques is just not possible. So we need to find other ways of being able to get reasonable approximations of these values without actually having to necessarily solve them, because that's not always possible to solve an integral exactly, but we can get approximations that'll give us a pretty good idea of these values. So we're going to start off talking about the midpoint rule. And the midpoint rule you can see in the graph down here. So instead of taking the left-hand side of each rectangle or the right-hand side of each rectangle, we're taking these intervals, cutting them in half, and using that midpoint to determine the height of the rectangle. Okay, so not the left hand or the right hand, but using the middle to determine the height of the rectangle. And as you can see, whereas like these ones on the left-hand side, right, those were under, those were over, right, these ones were over, these were under. With these rectangles, you're going to get some, we're going to get some areas that are over, some that are under, right? Some over, some under, some under, some over, like that. So these actually are going to do a better job of balancing out that area with the overestimates and the underestimates, and it's going to give us a better approximation of the area under the curve. So the midpoint rule says that the value of the integral from a to b of f of x dx is approximately equal to m sub n. So that's the notation we use for the midpoint with n subrectangles. And this is equal to delta x times f of x1 bar plus f of x2 bar, etc., etc., all the way up to fxn bar. And this is where delta x is b minus a over n, right? So that tells us how wide each rectangle is. And the x bar values, those are going to be the midpoints. So notationally, right, you take one of the x values plus the next x value and divide by 2. That's how we find the midpoint, right, of a segment. So this is just going to be the midpoint of the interval from x sub I minus 1 to x sub I. Okay, so when using the midpoint rule, we're able to, instead of doing left-hand side and right-hand side and like averaging them together, we just need to go in and find the midpoint first and use that as the height of our rectangle. Then we have the trapezoidal rule. Now you might be able to see here that the trapezoidal rule actually gives us a pretty good approximation here because we're drawing trapezoids instead of drawing rectangles. And by drawing trapezoids, we're lopping off those extra pieces that the rectangles would have counted if we had not looked at the curve more closely. So you can see even with the midpoint rule up here with those rectangles, Right? We do have some overestimates, some underestimates. With the trapezoidal rule, we try to hug the curve as closely as possible by drawing those line segments just to connect the different height values. So the way that we use the trapezoidal rule to approximate the integral, we get delta x over 2 times f of x sub 0 plus 2f of x sub 1 plus 2f of x sub 2, etc., etc. Okay, and then the coefficient of 2 goes all the way up to the second to last term, so x sub n minus 1, and then the last one does not have that coefficient of 2, just like the first one didn't. And this is where delta x, of course, means that same thing. So the interesting thing about this, and I have I have this x bar here. That should not be a bar. That should just be x. There we go. X sub I. Okay, so what this one is actually doing is it's actually taking the average of the left-hand side and the right-hand side. And if you think about those formulas for the left-hand side approximation would be starting with the leftmost value, right, at x sub 0, x sub 1, sub 2, all the way up to the second to last, right, sub n minus 1. Then, if we did the right-hand side, we would start at x sub 1, then x sub 2, all the way up to x sub n. So if we add those two together, all of the values would be double counted, except for the first one and the last one. Okay? And then to take the average of those two, we would divide by 2, because we're adding two values together. So that's what's actually going on with the trapezoidal rule. We're just averaging out the left-hand and right-hand approximations. Okay? And it's going to give us a fairly accurate value for this approximate integration. Okay? And like I said earlier, we often use methods like these to approximate integrals that we cannot compute directly. Right? So if we can compute the integral directly, then there's not really a lot of sense in using this. But just a disclaimer for this section. So note, in this section, we're actually going to work with a function we can integrate. We'll work with a function we can integrate. For the sake of ease. Okay, because we want to be able to compare what we get with the actual value, so we can see how accurate our approximations are. So again, we would use this generally for things we cannot compute directly, but we are in this case with these examples, we're going to work with one that we could compute directly, and we're just going to compare to see how good we're doing. Okay, so first up, use the trapezoidal rule and the midpoint rule with n equals 5 to approximate the integral from 1 to 2 of 1 over x dx. Okay, so first up, for the trapezoidal rule, we're using n equals 5. We're using a is 1, b is 2, right? Interval from 1 to 2. And so delta x, b minus a over n, that's 2 minus 1 over 5, which is 1/5, or just 0.2. Alright, so our integral from 1 to 2 of 1 over x dx is approximately equal to the trapezoidal approximation with 5 rectangles, which is going to be delta x over 2 times f of 1 plus 2 times f of 1.2, because again delta x is 0.2, so we're going up 0.2 every time, plus 2f of 1.4 plus 2f of 1.6. I'm going to cut it close here, plus 2f of 1.8 plus f of 2. Just fit it in there. Okay, so we've got, again, that first term and that last term are just coefficient of 1, and all the terms in the middle have a coefficient of 2. So then this gives us 0.2 over 2 is 0.1, and then we're inputting this into the function, right, the integrand, so 1 over x, so that's going to be 1 over 1 plus 2 over, so we've got it multiplied by 2, 2 over 1.2 plus 2 over 1.4 plus 2 over 1.6 plus 2 over 1.8 plus 1 over 2. Okay. And one thing you might be thinking is, like, this doesn't seem a whole lot simpler than just taking the integral. And again, I just reiterate that yes, in this case we could solve this integral directly, but we're practicing for potential integrals that we could not solve directly. So in this case, this would be really the only way to get an approximate value. So then this, if we just kind of plug and chug, run those numbers, we get approximately 0.695635 is what we get for our approximate value using the trapezoidal rule. Okay, then let's go ahead and look at the midpoint rule, and then we'll compare. So we need to identify where the midpoints are, right? So if we were looking at the graph of this, we would be basically, if we're going from 1 to 2, we'd be chopping them into these pieces with it starting at 1, then 1.2, 1.4, etc., etc. So when we're cutting those intervals in half, the halfway point, the midpoint between 1 and 1.2 is 1.1. Between 1.2 and 1.4 is 1.3, etc., etc. So midpoints of the subintervals are 1.1, 1.3, 1.5, 1.7, and 1.9. So our integral from 1 to 2 of 1 over x dx will be approximated by the midpoint rule with 5 rectangles. So that's going to be delta x times f of 1.1 plus f of 1.3 plus f of 1.5 plus f of 1.7 plus f of 1.9. Okay, delta x is still going to be that 0.2, or that 1/5. And we still have the function 1 over x as our integrand, so that's 1 over 1.1 plus 1 over 1.2, or excuse me, 1.3, plus 1 over 1.5, plus 1 over 1.7, plus 1 over 1.9. which is approximately 0.691908. So our approximations are not too far off, right? Depending on the level of accuracy you need. We got about 0.696 if you round, versus 0.692 if you round to only 3 decimal places. So that's pretty close. Again, it just depends on what level of accuracy you need, in which case we just use more rectangles, right? The more rectangles we use, the better approximation we get. So then we can compare these to the actual value. Again, because in this case we actually can find that. So the integral from 1 to 2 of 1 over x dx. Right, antiderivative is absolute value of ln of x from 1 to 2. So that's ln of 2 minus ln of 1. ln of 1 is just 0. So this is ln of 2, which we can get as approximately 0.693147. Okay, so we got 0.692 and about 0.696, and the actual value is about 0.693. So turns out we did a pretty good job, right? So if you only need to be accurate within a couple decimal places, then these were sufficient to get a good kind of bounding on that number. If you need to be more accurate, then again, just use more rectangles. So that's the midpoint rule and the trapezoidal rule for approximate integration. And now we're going to look at one more technique of approximate integration. This is Simpson's rule. Okay, Simpson's rule is actually going to be even more accurate than either of these previous two. So Simpson's rule says that the value of the integral is approximately equal to s sub n, which is Simpson's rule with n subrectangles, which is going to be delta x over 3. You might need a little space of this for this one, it's a little long, times we have f of x sub 0 plus 4 f of x sub 1 plus 2 f of x sub 2 plus 4 f of x sub 3, etc. And this pattern of 2, 4, 2, 4, 2, 4, etc. repeats all the way to the second to last term. So we get plus 2 f of x sub n minus 2 plus 4 f of x sub n minus 1 plus just a single term of f of x sub n. All right. So we have, again, first and last term are just singles. And then the pattern inside goes 4, 2, 4, 2, 4, 2, 4, 2, all the way from the second term to the second to last term. Okay. And it will always alternate 4, 2, and based on the number of rectangles that we have, it will always start and end with the 4s. Okay, so there will never be a case where it goes 2 and then the last one. That's just the way that it's set up, so you never have to worry about that. And this is where n, that number of rectangles, is even, and delta x is the same as it was before. This rule deals with what we call parabolic approximation. So whereas before we were looking at, here's the curve, and even with trapezoidal approximation, I was getting my heights and then drawing my straight lines here. Well, parabolic approximation if that's my curve. Basically, I am getting two values, and then I'm connecting them via some parabolic curve, like this. And you can see that obviously if I drew it a little more precisely, but this would give very accurate values, particularly for curves that are curvy, right? Not for lines, for example. So this one does give us a very good approximation in general. So let's look at the same example that we did before using Simpson's rule with n equals 10, because again we have to have an even number of rectangles to approximate the value of this integral. So we have our function f of x, right, is 1 over x, n is 10, and our delta x is going to be 0.1. Okay. And it's not 0.2 anymore because n is 10, right? Because I'm splitting the interval from 1 to 2 into 10 pieces, right? Or just b minus a over n, and you get the same thing. So we get the integral from 1 to 2 of 1 over x dx is approximately equal to s sub 10, which is delta x over 3 times f of 1 plus 4f of 1.1 plus 2f of 1.2, etc., etc. So I'm just going to put a little dot 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 in there. This goes all the way like plus 2f of 1.8 plus 4f of 1.9 plus f of 2. So as you can see with these approximate integrals, they can take up a lot of space, right? So particularly Simpson's rule, because we are using generally a larger number of rectangles because it has to be an even number. So this, if we fill this in, that's going to be 0.1 over 3, which I'm not going to simplify right now because that would not work out cleanly. It would give you an infinite repeating decimal. So we get 1 over 1 plus 4 over 1.2 plus 2 over 1.3 plus 4 over 1.4 plus 2 over 1.5 plus 4 over 1.6 plus 2 over 1.7 plus 4 over 1.8 plus 2 over 1.9. Oh, did I mess that up? 6. Did I skip something? Oh, I'm sorry. I skipped one. Right back there at the beginning. I went to all this trouble to tell you guys that it'll always end on 4. So this is a good way to check yourself. So we've got 1 over 1. I forgot the 1.1. So we got 4 over 1.1. There we go. Sorry about that, guys. Then 2, 4, 2, 4, 2, 4, 2, 4. There we go. And then plus 1 over 2. Okay, so that would be our fully expanded version of this, which then if we approximate that calculation, we get 0.693150 is the approximate value we get using Simpson's rule. And then just recall from just a minute ago, we already looked up what the actual value of the integral is. It's 0.693147. And you compare that to this. Notice we were good to 5 decimals if you round this. Actually, if you round it, then they're the same number. Okay, but If we even just up to 4 decimals, it's identical. Right, so we got a much better approximation here using Simpson's rule. So notice that, again, Simpson's rule got us a much closer approximation. And the reason that it's able to do this is because Simpson's rule actually gives us a weighted average of trapezoidal and midpoint rules. So this is not something you're going to have to deal with much. This is just for your information. But when you take Simpson's rule, what you're actually doing is you're taking the trapezoidal approximation and the midpoint approximation. You're giving them particular weight. So you're weighing the midpoint as 2/3 weight, and the trapezoidal weight has basically 1/3 of the input on what that approximate value is. Okay? And then adding those values together actually give us this very, very accurate approximation. Okay? So that brings us to the end of section 7.7, dealing with approximate integration. So again, a tool very useful for us, particularly with integration that we cannot solve directly. So that's all I have for you all in this section. We will be back soon with section 7.8.